Hey everyone, it's Mr. Canfield. You might notice some fun shadows. I will try to get out of the way as much as I can. I'm filming at night, so I don't have as much natural light. Burning the midnight oil, so to speak. So today we're looking at our last new method of integration called integration by partial fractions. I like to call it partial fraction decomposition because that makes it sound even more fun. So we've learned U substitution, we've learned integration by parts, we've learned other formulas and stuff. So this is one last way that we can rewrite an integral and make it look really nice. So let's say we have 8x plus 82 over x squared plus 3x minus 10 dx. So we could go at this a few different ways. One of those would be to, let me actually go to a separate piece of paper because I'm going to do this in ways that don't work out for us. So like if we try U substitution, let's say U is equal to the denominator. That's something that we've tried before. So our du then would be what? 2x plus 3 dx. And then if I go back and I do my substitution, I'm not sure if you can see it, but the 8x plus 82 isn't going to wind up canceling out in ways that we're used to. And it leaves us with something that's not quite workable. So then, well, maybe you're thinking, well, I could think about this as 8x plus 82 times 1 over x squared plus 3x minus 10. Could I do a parts on this? And I'm not gonna lie, I'm gonna do like kind of a half-hearted effort here, but let's see. Let's say U is equal to the 1 over x squared plus 3x minus 10. That would make du equal to, so this is to the negative first power right now, and I'm just kind of spitballing, so I'm gonna go kind of quickly. So that'd be what? Negative 2x plus 3 over x squared plus 3x minus 10 squared dx. And then our dv would be 8x plus 82 dx, which would make v, what was that, 4x squared plus 82x. So then when I go and do my parts formula, I'll do u times v minus v du, right? So my v is going to be what? 4x squared plus 82x. Have I like made my point yet? This is worse than what we started with. So surely there must be a better way. There is. And don't call me Shirley. Anyone? All right. So here's the way that we really do this. We take this fraction and we break it up into two separate fractions using a technique called partial fraction decomposition. Here's what I mean. It's really simple. If I have something like 3/4, I could write 3/4 like this. I could write it as 1 over 1 minus 1 over 4. That would get me 3/4. Another way that would get me 3/4 is 1 over 2 plus 1 over 4. Or if I had like 3/8, I could rewrite 3/8 as two different fractions and call this like a half, and then do minus 1/4, and that gives me 3/8. And with numbers, we can do this sort of thing and rewrite fractions. But we can do the same thing with algebraic expressions. The key was to figure out different factors of our denominator. So if you've never done this technique before, don't worry. The first time I did it was the first year that I taught BC Calculus. So some people learn this in Algebra 2. So maybe you learned it in Algebra 2. I did not. And I didn't learn it in college. So here's the way it works. Let's factor x squared plus 3x minus 10. So remember, we're looking for factors of 10 that add up to 3. Well, net factors of negative 10. So we know one's plus and one's minus. So let's see. Well, I know one's 5 and one's 2, because 5 times 2 is 10, and then if I make 5 positive and 2 negative, then they'll add up to positive 3. Okay, so what we are going to do is we're going to say something over x plus 5 plus something over x minus 2 equals 8x plus 82. I'm going to go through the long version the first time, and then I'm going to show you the shortcut, and we're never going to look at the long version ever again. So long version is as follows, right? This is A, this is B. So I know that A times x minus 2 plus B times x plus 5, I could then put all over this. And in case you missed that, we have, like I have to multiply this by x minus 2 over x minus 2 and x plus 5 over x plus 5. So oops. So then our numerator looks like what? Ax minus 2a plus bx plus 5b. So let's talk about things that we know. So this is our numerator, right? Well, then that means we know that 8x plus 82 is equal to ax minus 2a plus bx plus 5b. So we could say that 8x is equal to ax plus bx, or we could just say that 8 is equal to a plus b, assuming x is not 0 for this situation. And we also know that, what, 82 is equal to negative 2a plus 5b? Well, then can't I just do a linear combination? I could multiply the top by 2. If I do that, I get 16 and then 2a plus 2b. So those cancel. 82 plus 16 is what, 98. 98 is equal to 7b. 7 goes into 98. 10 times is 70. 28 more is 4, so 14. So b is 14. And then I can back solve. And a plus b is 8, so then that would make a negative 6. And lo and behold, we have a and b. And I never do this method. Okay, yep, I was just double checking. Cool, so I got the same answers as Stu did. We're never gonna do that, but that's how we did it this time. We're gonna do a shortcut. I'll show you the shortcut after we do this example. So b was 14, a was negative 6. All right, what? Negative 6 is 5 plus 14 over x minus 2. So here's the cool thing. The integral of the sum is the same as the sum of the integrals. So I could say this is this and this are the same, like if I do that, or I could just look at them individually, like that. But this, I broke up into that they are the same thing. If we combine these two fractions, we would end up with what we started with. And you might be like, well, what's the big deal? What's so helpful about that? Well, check this out. This is -6 over that, right? Well, I could pull a -6 out then. That would leave a 1 on top. And then I could do the same thing. I could pull the 14 out here. These are baby integrals. 1 over x plus 5. What did I take the derivative of to get that? Why, the natural log, that's what. Same thing here. And we're done. So the trick here is if I can figure out how to break this up, feel free to use the method I just used, but I'm going to show you a shortcut that is much faster. Then the integrals are super simple. So I'm going to do the same thing, but with this alternative method. So still factor it the same way that we would. So x plus 5 times x minus 2. So it almost seems like magic what we're about to do. So here's what I do. Sleight of hand. First thing I'm going to do, I'm going to cover up one of them. What is the 0 of the thing I just covered up? That's what I ask myself. So I just covered up x plus 5. What's the 0 of x plus 5? Remember, that's the thing that makes x plus 5 equal to 0. So I subtract the 5 from both sides and I get x is equal to -5. What you do is you plug -5 into what you see. So that would be 8 times -5 plus 82 all over -5 minus 2. So let's see, that's going to be 8 times, that's -40 plus 82. It's 42 over -5 minus 2 is -7. And 42 over -7 is -6. And so the one that I covered up, that's where I fill it in. We do the same thing. We're going to cover this up. So I'm going to cover up the other one and ask myself, what is the 0 of that? Well, the 0 of that is 2, right? Because x minus 2, I add the 2 to both sides. And then I proceed to plug 2 into what is still visible. So let's see, that's 16 plus 82, that's 98. 98 divided by 7. Gee, I feel like I just did that a minute ago. We get 14, and it always goes above the one that you just covered up. So this is detailed in our notes. That's actually where I learned it. I love this shortcut. It makes these problems super easy. People seem to like partial fractions in general. Unless you suck at factoring. Sorry, unless you stink at factoring. Even that's too negative. Sorry, unless you in factoring have a storied past, a tumultuous relationship. If you're not on speaking terms. So anyway, with this one, I would just say go try it. Don't wait for me to do it. People tend to mix up the moving parts of this. That just comes from a lack of practice. So if I do this one, let's factor the denominator. X. It works for ones that don't just start with a plain x squared. These are just easier to factor. So one's going to be 5, one's going to be 1, because 5 times 1 is 5. Oh, they're both negative. Okay. So let's see. So I'll cover up my x minus 5, and that means that whatever I get is going to go above x minus 5, and I'll plug in 5 to what I have left. So 5 minus 4 is 1. 5 minus 1 is 4. Don't care about that right now. It's fine. It's fine that it's a fraction. We're actually going to see something kind of funny. There's a pattern that happens with these a lot of the time. All right. So x minus 1, so we'll plug in 1 to what we see, right? So on the top, that'll be what? 1 minus 4 is negative 3. On the bottom, 1 minus 5 is negative 4. Wait. Yeah, okay. So 3 over 4, oh, they're both positive. Oh, well, that's pretty sweet. 1/4, 3/4. I noticed a lot of the examples that we do wind up having these kind of complementary pairs. I'm going to pull the 1/4 and the 3/4 out front of their respective derivatives, or integrals, sorry. But I wouldn't even write this step on my own paper. I would just jump straight to the answer. Because the less writing I can do, the more time I save. So that'll just be 1/4 times the natural log of the absolute value of x minus 5 plus 3/4 times the natural log of the absolute value of x. All right. My my pen was not making the strokes I was trying to make, but I managed to get it to work. Okay. It's not underneath it. Does that work? See, I don't know why I'm asking you that question, because like you can't audibly respond to me right now. Well, maybe you did, but that'd be kind of weird. All right, number 3. Let's look at this one. So I'm going to start to speed up just a little bit. Just slow down the playback speed if it's too fast. So let's see, I can see that this factors to x. 10 and 2 don't work, but 5 and 4 will. Looks like we can subtract the 5 and add the 4. So I'm going to try to do this as I would actually do on my own paper. So when I plug in 5, I get 2 over 9. And then when I plug in negative 4, I get 2 over negative 9. And my work right now is not super proper, but I can jump to the final answer now. Just like we did last time, where we pull the fraction out front and then it's going to be just the natural log. Well, I can just do that in one step, and I'll be a little bit more proper, and I'll do that. How's that? Ooh, much more proper. So I get 2/9 times the natural log absolute value x minus 5 minus 2/9 times the natural log the absolute value of x plus 4 plus c. All right. I did write my plus c. I know it was off camera, but I swear it was there. I promise. All right. All right. So something you might notice is that every time we've done these, the power of the, oh, excuse me, I'm putting myself to sleep with my calm voice. the degree of the numerator has always been less than the degree of the denominator. We're going to see one that's not quite like that later, and see what to do with that. So, but anyway, this one, we can do the same kind of thing. Oh, factoring this denominator, looks like I get x times x squared minus 4. But be careful, x squared minus 4, that actually factors into two different linear factors, x plus 2 and x minus 2. So we've got like an A, B, and C situation here. The trick still applies, it still works the exact same way. So let me just write this out one more time, just so we can look at it a little bit easier. So if I'm doing this, I'll cover up the x and plug in its 0 to everything that I see. Well, the 0 of x is just 0, so when I plug it in, all that goes away. I'm just left with 12 on top, and on the bottom I'm left with a 2 and a negative 2. So when I plug in 0, I get 12 over negative 4. That's negative 3. Then I will plug in the 0 for that one, which is negative 2. So if I do that, well, negative 2 squared is 4 minus 24 plus 12 over, you can see an x and an x minus 2. That's negative 2, negative 4 on the bottom. So let's see, it's negative 20 plus 12 is negative 8 over positive 8, negative 1. And then we'll cover up the x minus 2, plug in a 2 to everything. And so this time, let's get a 16 plus 24, looks like that's 40 over 8, which is 5. And so now we have these three separate integrals that we can break this up into. Three separate, all equally easy. Negative 3 ln absolute value of x minus 1 ln absolute value of x plus 2 plus 5 ln absolute value of x minus 2. Oops. Then plus c. And hooray. Cool. All right, let's see what's next. In the AP exam, do you mean on the AP exam? You are only responsible for partial fraction integration where denominators factor into non-repeating linear fractions. Oh, excuse me. So we can see stranger ones, and there's a non-essentials portion of our book that I don't go over because it's not essential. But then we have this one. So this one, since the top has a higher power, partial fraction decomposition doesn't actually work. If we did like our little trick here, we would get numbers, oh, excuse me, but they wouldn't actually be the right numbers. So this is not common for our purposes, but what I would need to do is long division, where we put the bottom out front, the top inside, and then you go through and do the long division. Cool, so once you have that, no, just kidding. So that's where we say, okay, how many times does x squared go into x cubed? It goes in x times. And so my first number that I have up here is an x. And I multiply all those by x, which gives me x cubed minus 6x squared plus 5x. Then we subtract, right? Be careful, we're subtracting all these, which means all their signs change. So x cubed minus x cubed goes away. Then negative 9x squared minus negative, so it's a positive, we're adding 6x squared to it, so that's negative 3x squared. And then 24 minus 5x is plus 19x minus 17. And then we ask ourselves, how many times does x squared go into negative 3x squared? It goes in negative 3 times. And when we do that, we'll take the negative 3 times all these. We'll get negative 3x squared plus 18x minus 15. We'll subtract now. Those will cancel. We'll be left with 1x here. We'll be left with minus 2 here. So that's our remainder. So what I can do, well, the reason I knew that, sorry, is because x squared does not go into x minus 2. So I actually could rewrite this as this divided by this is equal to x minus 3 plus our remainder. Our remainder is x minus 2 over our original denominator. And now all I have to do is partial, all I have to do, right after all that, all I have to do is partial fraction decomposition on this guy, and that'll lead us to an easy integral for this. So it's going to wind up being, what, x squared over 2 minus 3x plus, and then we'll have to go and do the work for that part. And I think I'm too tired to skip it. I'm just kind of in autopilot mode. So the denominator, what, x minus 5 and x minus 1. We saw that denominator a couple minutes ago, but this is a different numerator. So when I do that, we'll cover up the minus 5. So we'll plug in 5 to both of those and get 3 over 4. And then I'll plug in 1 to both of them and get negative 1 over negative 4, or 1/4. So this one will be, what, 3/4 ln. And this one will be 1/4 ln. Maeve is currently sleeping on Mrs. Canfield, but she just whispered over to me, who is Ellen? Like, if she doesn't want to watch her show, that's her business. Especially after all that fallout this year, right? Sorry, too topical. That means I'm going to have to re-record this video at some point in the future. I can't just use this for the rest of my career. You might not even know who Ellen is anymore. Maybe she got canceled by this point. Or maybe she's president now. All right. Sometimes we can use substitution in order to integrate expressions that do not seem integrable. That's what that said. Integrable. All right. So excuse me. These questions are a little silly. And this just leads us into a discussion kind of about how integrals are not a set process. We've kind of treated them like that, like, oh, today we're doing U-subs problems. Today we're doing integration by parts problems. Today we're doing integration by partial fractions problems. The way that it really works is you'll get an integral and you might stare at it for a long time and not know, well, what direction do I go? I have these different techniques, but it might not be any of those techniques. It might be one that you've never learned before, or it might be a bizarre combination of them. And sometimes you just have to be clever. And I would not know how to do this if he didn't give us this hint. This is more to show you this is a technique that could be used to then integrate it. So check it out. If we said u is equal to e to the x like he suggests, then we get u over u minus 1 times u plus 6 d x. It's still dx. Let me see. Oh, right. So instead of saying u dx, I actually could say, so I can replace dx with du over e to the x, right? And that u is still an e to the x, and so we can cancel those. So we can actually change this into 1 over u minus 1 times u plus 6 du. And now it's a really easy problem. So, like if I do that, then, you know, plug in the 1, we get 1 over, excuse me, 1 over 7. So 1 over 7 ln u minus 1 plus, and then plug in negative 6 and get, oh, negative 1/7. And then we can rewrite this as 1 over 7 natural log of e to the x minus 1 minus 1 over 7 natural log e to the x plus 6 plus c. Tricky, tricky. 7 is more of the same. You do the same kind of thing. The numerator will cancel out. Winds up being this nice little thing. You factor. It's going to be what, u squared plus u, and factor u out. So I'm not going to continue on that. Seems a little repetitive. And I think that first example, we get the idea. Number 8 says find the shaded area, and our function is y is equal to 80 over x squared plus 6x plus 8. Well, the shaded area is just the integral. So this would be the integral from 0 to 2, 3, 4 of 80 over x squared plus 6x plus 8 dx. If you've watched this far and you're not sure how we would do partial fraction decomposition on this, I guess let me know. I can help you out. It's more of the same at this point. Just at the end, you know, we get blah, blah, blah. Then we plug in 0, 4. Right? So we plug in 4, plug 4 stuff in, minus, plug in 0. Hashtag answer, no, equals some number, right? What about, oh, this one? On this one, looks like they're intersecting at 4 and negative 4. We're going to have to do top minus bottom here to find the area between the two things. In this case, the top is the line y is equal to, I haven't the foggiest, but the bottom looks to be 9 over 25 minus x squared. Well, if they intersect when x is 4, 25 minus x squared, 25 minus 16 is, oh, it's 1. It's 1. And if you're like, why is this in here? Well, 9 over 25 minus x squared is 9 over 5 plus x times 5 minus x. And I can do partial fraction decomposition, get a nice easy integral, plug in the 4s. Yeah. Let's see. A person with norovirus boards a cruise ship of 2,000 susceptible people. Stu's not very nice. He just wants everyone to get sick. Let X be the number of newly infected people at time T. Too topical? Too current? This is BC.
Thank goodness this is too hard for algebra.
You know, this is AP Calculus BC.
I can't follow along. I didn't learn anything this semester.
I didn't learn this until I graduated from college. Mrs. Canfield thought I was recording an algebra video, and she was like, this is too hard for algebra. Let X be the number of newly infected people at time T. The neurovirus spreads at a rate proportional to the product of the total number of infected. This sentence right here, this is like AP code for, is it the next chapter? Is logistic growth the next chapter? Nope. This is AP code for logistic growth. This is called a logistic growth curve. We will talk more about that in the future. So this says solve the DEQ, solve the differential equation. So as much as I want to skip this, I'm not going to. dx dt. K. All right, be careful here. This is not dy dx, this is dx dt. So essentially, x is like where y normally goes. All right, so here's how we solve something like this. We can multiply both sides by dt. So we have a dx over here. K, x plus 1, 2,000 minus x dt. We want to get our variables on the same side as the variables that they care about. So like these x's and this t, like they're not the same variable. The x's are over here. So we'll divide by this. So over here on the right side, we have k dt, and on the left side, we have 1 over x plus 1, 2,000 minus x dx. And solving a differential equation, what you do is you go bop, bop. You do bop, bop. You integrate both sides. Right-hand side, super complicated, kt plus c. Whoa, that was a lot. Left-hand side, hey look, you can do partial fraction decomposition here. It's almost like that's the section that we're in. So let's see, if I cover up the -1 and plug in -1, then it's 1 over 2001. A Space Odyssey. You know, that came into my head too, Mrs. Canfield. I personally did not get as much out of 2001: A Space Odyssey as some people. I think Full Metal Jacket was more impactful for me from Stanley Kubrick. All of his movies are jarring. I wouldn't recommend them if you're easily...
Did he do a Clockwork Orange?
Yeah, he did a Clockwork Orange. You're not allowed to watch a Clockwork Orange.
My mom said I couldn't watch it when I was in high school, and I still haven't.
I think that's a good choice. It's fairly disturbing.
Yeah, they're also, these kids aren't, well, I guess they're 17. You can watch R-rated movies.
Yeah, and the Shining is another one that Kubrick directed. You know, I'm not recommending any of these. I'm just saying that I've watched most of them. I guess I watched all of his movies. Well, I mean, I think he's done other movies besides. Anyway, so there's that one. Why did I put the 2001? I got distracted. 2001, 1 over the x plus 1. And then we'll plug in 2,000 to that one. And that'll be 1 over, oh no, I was right. And then that'll be 2,000 here, so. We'll plug, yeah, 2,000, so it'll be, oh, it's the same thing. My brain's melting a little bit. Let me just make sure I didn't do a silly. So I plugged in 2,000. That was 1 over 2001. That should have gone over the 2,000. Then I plugged in -1. Same number. Okay, okay. All right. So that's what we get. So we can say 1 over 2,000. Oh, you know, we can even factor that out of both of them and just say ln of x plus 1 plus ln 2,000 minus x. And there's a plus c on this side, but remember when there's a plus c on both sides, we can just say there's a singular plus c on one side that kind of accounts for all of them. And then he said, please don't solve this for x. Solving this for x would be a little bit of a nightmare. Much like the main character in 2001: A Space Odyssey experiences on the space station. Some real groundbreaking special effects in there from a long time before any of us were born. So, the homework, 18 problems. I don't need you to do all of them. Take your pick. Do the evens or do the odds. If you must, feel free to do all of them, but half is enough for me. I feel like once you've been through the notes and you've been through half of the homework like this, you get it. You either get it or you don't, and if you're not getting it, let me help you. Everyone can get this. These can be really straightforward. I know this problem was kind of weird, and some of the last ones we were doing were kind of weird, but most of these should be nice and straightforward. So, all right, everybody, have a great rest of your day. Bye.